Okay, so in this video, I want to look at one more short application of the fundamental theorem of calculus in having a definite integral where the bounds of integration are variable functions of x and asking what is the derivative of this strange looking function of x. First, let me just really quickly review the relationship between the indefinite integral and the derivative. So if you remember, by definition, when we write integral of f of x dx, the indefinite integral, we are asking for all antiderivatives of lowercase f of x. So the answer is big F of x plus c, where, of course, uppercase f is an antiderivative of lowercase f. So if you differentiate your answer, you should get back the original function. And of course, this is the inverse of integration, the inverse of differentiation, sorry. So, what if we then integrate the derivative of f? So we have, imagine you have f, you first differentiate it, and then you integrate it back. Well, what do we get? Well, think of it. We are looking for a function whose derivative is the original function. So what function has as a derivative the derivative of f of x? Well, obviously, f of x itself. If you differentiate f of x, you get the derivative of f of x, right? This is a trivial statement. So you see, if you have the function f, if you differentiate first, then you integrate, you get back the function f up to a constant. What if we do the opposite, right? So what if we had f of x, then we integrated f of x first, and then found the derivative of the integral with respect to x. So we're doing the opposite. Here we had f, we took its derivative, then we integrated, we got f back up to a constant. Now we're doing the opposite. Take f of x, integrate it first, then differentiate. Well, what will come out? Well, replace the indefinite integral of f in this form, so uppercase f of x plus c. The derivative of big F is just f prime, plus the derivative of a constant is 0, but f prime of x is lowercase f of x. So, the derivative is the opposite of the integral, and the integral is the opposite of the derivative. So if you differentiate the function, then integrate, you get the function back up to a constant. If you integrate the function, then differentiate, you get the function back. Just to show you how we can monkey around with derivatives and the indefinite integral. We can play the same game with the definite integral in this order. So let me show you the general principle, and then we'll look at an actual example. Look at the following function of x. I'll call this g of x. So big G. Suppose I integrate the function f of t, and I'll use a different variable, f of t dt, from 2 points, but where the endpoints of integration are variables, functions. They're functions of x. So I'll call the first function a of x, and the second function b of x. And this really is a function of x and not of t. Because if you remember, all we're saying here, if you think of the definition of the definite integral, we are asking for the net area below f between ax and bx. So the variable t here is a dummy variable. It can be replaced by any variable other than x. So I could write this as the integral from ax to bx. Instead of t, I could use z. I could say f of z dz. Or, give you one last example, I could again integrate from ax to bx, and I could replace z by u, f of u du. All of these three mean the same thing. You want the net area below f between the points ax and bx. So when you see something like this, always remember that it is a function of the variable in the bounds of integration, not in the integrand, as the variable in the integrand is a dummy variable when it comes to a definite integral. So now we have this function of x. We can ask, what is its derivative? So what is g prime of x equal to? How do we differentiate something like this? Now it looks a bit scary. It's actually not too bad if we first rewrite this using the fundamental theorem of calculus, which says to find a definite integral, all you need is an antiderivative of the original function. So you need to find a function uppercase f whose derivative is the same as the function you are trying to integrate. So suppose we have such a function. So we find a function uppercase f that is an antiderivative of lowercase f. So if we differentiate our function, we get the function we're trying to integrate. Well, now we can apply very simply the fundamental theorem of calculus. So g of x being the definite integral of the function f from ax to bx. Well, what does FTC say, right? FTC being the fundamental theorem of calculus. Once you have the antiderivative, the function whose derivative is the function you're trying to integrate, all you do is you find the antiderivative at the upper bound of integration, so f of b of x, minus the antiderivative at the lower bound, f of a of x. And that's it. So now when you think of differentiating something like this, which looks kind of scary, ignore it. Differentiate g by differentiating this expression now, again coming from the fundamental theorem of calculus. And you'll see this is quite easy. It's just a chain rule. So we want the derivative of g of x, so g prime of x. Well, as g of x equals this from FTC, we'll differentiate this now, and we'll ignore this. So we want the derivative of f of b of x minus f of a of x. And all we got to do here is differentiate carefully, remembering the chain rule. As we have a composition, this is f of b of x, this is f of a of x. So we have in both cases a composition, so when we differentiate, we must apply the chain rule. The chain rule says, as you remember, or you should remember, is you differentiate from the outside function and you work your way inward to the inner function. Well, the outside function is big F, so we differentiate big F, we get f prime at b of x. But this is just a derivative of the first layer of f. There's still b of x left over. The chain rule says you must multiply whatever you have so far by the derivative of what's left over. What's left over is b of x. Differentiate, you get b prime of x. There is nothing left over, so this completes the differentiation of f of b of x. Minus, well, this is trivial now. It's just f of a of x. Same thing as this one, but replace replace b by a. So we have f prime at a of x times chain rule a prime of x. Now we have the derivative, but we can simplify further, as big F prime is just lowercase f, as f is an antiderivative of lowercase f. So what are we left with? G prime of x. The derivative of this integral is just replaced now, uppercase f prime by lowercase f, so it's just f of b of x times b prime of x minus lowercase f of a of x times a prime of x. And that's it. So let me give you an example of, or two examples of this, just to show you that this is very straightforward once you think of rewriting the definite integral using the fundamental theorem of calculus. And you don't even have to remember this. Every example You can basically rederive the result. Go from the integral to the equality from the fundamental theorem of calculus, then differentiate slowly with the chain rule, and then simplify. Let's do two short examples. In both of my examples, I will show you the whole derivation again. So I do not want you to remember this formula, because if you try and remember it, you'll forget it, it won't make sense, and there's no point in remembering something that is a straightforward application of the fundamental theorem of calculus and the chain rule. You should know both of these, and you should know, of course, when to apply them. So, suppose that g of x, our first example, let's integrate from x squared to x cubed. Let's go with sine of t to the 4 dt. So, again, let us, before we differentiate, rewrite this with the fundamental theorem of calculus. This will be the antiderivative at x cubed minus our antiderivative at x squared. And again, be explicit. What is big F here? Well, it's a function whose derivative, big prime, sorry, but it's a prime, is the function you're trying to integrate. Well, we're trying to integrate sine of t to the 4, so f prime of t is sine of t to the 4. So that is your function. Alright, now that we have this equality, we will find the derivative of g by differentiating this. So g prime of x equals the derivative of this. Chain rule, as we have a composition, f of x cubed minus f of x squared. So derivative of the outside, f prime of what of x cubed? Chain rule times the derivative of what's left over, which is 3x squared. Minus, we repeat, the derivative of the outside function, big F prime, of what of x squared, times the derivative of x squared, chain rule, 2x. Now we're basically done. Two substitutions. F prime of t is sine of t to the 4 for any t. Well, here we have a simple substitution. We have f prime of x cubed, not f prime of t, so replace t everywhere by x cubed, which will give you sine of x cubed to the 4th power. But if you take x cubed to the 4, it's x to the 3 times 4, which is 12. So sine of x to the 12 times 3x squared minus another substitution, f prime of x squared. Now replacing t by x squared, but x squared to the 4 is x to the 2 times 4, which is x to the 8, times, of course, the 2x. If you want in the end, I mean, not much of a simplification, but you can factor in x, the only common term between the two terms, and you're left with 3x sine of x cubed, sine of x to the 12, sorry, minus 2 sine of x to the 8. And there you have it. So as a function of x, the derivative of this function is this function. And what was nice about this is we did not have to evaluate the integral. We didn't have to find the antiderivative. We just said, well, if we had an antiderivative, here's how we would do it. And once we differentiate f, it becomes f prime, which we know. So you see, nowhere in our solution have we figured out what is f. All we need to know when it comes to differentiation is that as f is an antiderivative, its derivative is the function we're trying to integrate. And actually integrating sine of t to the 4, not an easy thing to do. Alright, let's do one other short example. Instead of t now, I'll use a different variable to really emphasize that what we have is a function of x, and this variable here is a dummy variable. So what if I integrate, say, from sine of x to root of x, e to the u squared du. Again, u here is a dummy variable, x is the key variable, so g is a function of x. Again, before we differentiate, we want to bypass the integral in favor of the fundamental theorem of calculus, so the antiderivative at the upper bound minus the antiderivative at the lower bound. And we are explicit the derivative of our function, function of u, the derivative of our uppercase f function is of course e to the u squared. As uppercase f is an antiderivative of e to the u squared, its derivative as a function of u is the original function. And now we bypass the integral and we differentiate g using this form. So g prime of x is the derivative of this chain rule, derivative of f prime of what? Of root of x, such as the derivative of big F by the chain rule times the derivative of root of x, which is 1 over 2 root of x, minus the derivative of the outside function f prime of what? Of sine of x. Chain rule times the derivative of what's left over, the derivative of sine of x is cos of x. Once again, we now have to make a substitution. We want f prime of root of x and f prime of sine of x, we just replace. F prime of u is e to the u squared for any u. We are now replacing u by root of x. So we get e to the root of x all squared, but root of x squared is just x. So we have e to the x over 2 root of x minus f prime at sine of x, now replacing u by sine of x, e to the sine of x all squared, e to the sine squared of x, times cos of x. No common factor, we can't factor anything out, so that's it. So the derivative of this, again, rather strange looking integral, being a function of x, is e to the x over 2 root of x minus e to the sine squared of x times cos of x. So there you have it. An application of how we can differentiate these bizarre looking functions of x using the fundamental theorem of calculus and of course the chain rule.